To talk a little bit more about the electromagnetic spectrum. We already talked about radio waves. We talked about what a microwave was and what an infrared wave was. There's a table on page 49 and 50 that you guys can try to fill out, which you guys just follow your notes and fill out this. All of this can be filled out, this table, by looking at the notes I have posted for you. And just that's all you need to do when you are filling. It's really straightforward, really easy, but you have to look at my own notes. So look at the physics notes, and I want you to fill in the blanks for page 49 and 50 about all the properties of all of these waves. Okay, so I already talked a little bit about radio, microwave, infrared. I'm just going to go a little bit deeper into visible light. So visible light rays coming from the sun, right? So here's the sun, and then one part of the sunlight is the visible light rays. Okay, so visible light rays come from the sun, and this is what allows us to see, right? So you guys know the sun emits infrared waves because you guys can feel the heat coming from the sun, right? But we can't see infrared waves. We can only see the visible light rays that are coming from the sun, and those operate within a very narrow frequency, and it actually tells you on page 3, and it's called like Roy G. Biv. Red, orange, yellow, green, indigo, blue, and violet. Red is 700 nanometers. Violet is 400 nanometers. So basically red at 700 nanometers is like this long, and violet is like this long, 400 nanometers. 400 nanometers means that the frequency, like the wavelength, is closer together. And so like Roy GBIF, like you guys should know, like red, orange, yellow, green, blue, indigo, violet, that's what it stands for. So the highest frequency is violet. So if you have a violet flame, it's going to be higher frequency, it's going to be hotter than a red flame, right? And so this is what we perceive as color, right? And it's coming from the sun, and any light, including the light in your home, will emit this visible light so you can see. And when you turn the light off, no longer can you see, because no longer this Roy G. Biv, and that's like when the sun goes down and it's dark outside, so the sun is not emitting the visible light spectrum anymore, so that's why it looks dark outside, right? So anyways, if you look at visible light, you guys got to know that light has specific properties. So light can be reflected. And so when I say light can be reflected, imagine this is a mirror, right? And here's the incoming light ray, and it's being reflected like this, okay? So this light, right, you guys got to know, like this, like imagine this is the sun, the light comes in, hits in, like that's like you looking into a mirror, the light hits perfect. This line coming in is called the angle of incidence. So this is this line coming in. This line here is called the I just saw something here. So let me just start again. This here is called the incident ray. It's not an angle. We haven't dealt with the angles yet. This here, is called the reflected ray. Okay, so the incident ray is the ray of light coming in, and the reflected ray is the ray of light that's being reflected. This here that I'm drawing right here is called the normal. Okay, so the incident ray hits the normal, and then it's reflected and becomes the reflected ray. And this here is called the angle of incidence. And the angle of incidence is just the incident ray, right, to the normal. And then there's another one. This one is called the angle of reflection. So this is the angle of the reflected ray, right, from the normal. And actually the angle of incident equals the angle of reflection. Okay, so if this is like 30 degrees, then this is also 30 degrees. So they equal each other. And that's what you need to know about reflection, right? The incident ray and the reflected ray are, you know, if it's coming in at 30 degrees, it's also coming out. And they all, this is the plane here, this is the plane mirror that they're landing on. And anyways, that's basically all you need to know for that. You need to know what refraction is. So refraction is just a phenomenon that happens because, like, if you have light Imagine this is light coming from the air, and this light hits the water. The water actually makes the light bend. And so this is what I call refraction, okay? And because the bending of light happens, like, so imagine this is water, right? Things kind of look funny. Just like if you're sitting in water, your legs look like they're like different, right? They almost look like contorted, distorted, right? And that's just because of the angle of the light coming in. It's being refracted. It causes everything to look funny, okay? So that's pretty much all you need to know for refraction. And then you have a phenomenon called diffraction. So diffraction just means this. You have a gap, right? And then you have like, let's say you have like sound, right? So basically, if you have a sound wave, and this is diffraction. Oh no, how did that happen? Okay, so let me do this again. Okay, so there's this gap. Here's a gap here. Here's the gap here. Okay, so let's say I have a wave, sound waves, right, traveling through the gap. So let's say all these sound waves travel through this gap, but there's not going to be very much diffraction. So diffraction just means like these wavelengths like kind of spread out as they pass through the gap. But let's say like you get a single wavelength of light here. Basically, if you can narrow the gap so that it's equal to like a wavelength of light, you're going to get the most diffraction occurring, right? You want the gap to equal the wavelength of sound coming in. So if this is the wavelength of sound and the sound actually equals the size of the gap, you're going to get what we call maximum diffraction, which is the sort of spreading out of the sound, right? If the gap is really big and this whole thing kind of travels through, then you're not going to get as much diffraction. You're going to get less of these waves sort of spreading out from the gap. That is diffraction, and you can see a diagram of it on page 53. For polarization, you guys have to know, and I told you guys that light travels as electromagnetic. Okay, so when light travels as electromagnetic, you have like one part of light that is like the electro part, right, which is like the moving electrons, and then you have another part which is kind of like the magnetic part of the electromagnetic spectrum. So you have like two parts to the electromagnetic spectrum. And if you like wear polarized sunglasses, the polarized sunglasses only lets like one wavelength through. Like let's say it only allows this electro wavelength through, but it blocks the magnetic. So things don't look as like, things don't look in color. Like things are not in color. They're like sort of, you know, when you put your polarized sunglasses, everything kind of looks a little dimmer, a little darker, and that's because you're blocking out one of the rays of the electromagnetic spectrum. Either you block the magnetic ray or you block the electro ray. And that's what polarization means, okay? So that's basically all you need to know for that. And you can try the practice problems on page 54 and 55. You can try them and see how you do. And we just have one more lesson, which is the history of the universe, and we're done.